Good afternoon, class. We are looking at practice test number 2, covering module 2, chapters 3 and 4, chapter 4, exponential and logarithmic functions. Here's part 2. Expand each log as much as possible, reminding you of the logarithmic properties. Y equals log x base b means b to the power of y equals x, and therefore log 1 with any base is 0, log b base b is 1, log of b to the power of x base b is x, b to the power of log x base b is equal to x. And numbers 3 and 4 refer to the fact that the two functions, logarithmic functions and exponential function, are inverse functions. Log xy base b equals log x base b plus log y base b. The product rule, the quotient rule, log of x over y is log x minus log y. All of them have the same base. And finally, the power rule, log of x to the power of n base b is n log x base b. So in this case, we're going to cut it into three parts by simply using number 5, log x plus log y plus log z, and all of them have the same base, namely 7. What about here? ln 9 minus ln x, we are using number 6, the quotient rule. Log of y to the power of 10, we're going to use number 7, the power rule. We're going to put the 10 in front. We get 10 log y. Now this one, we are going to use, actually you can do it in one shot, but we're going to use first number 5, the number 6, the quotient rule, log of the top minus log of the bottom. So log base x of a squared b to the power of 4 minus log base of c to the power of 7. So first we use number 6, the quotient rule. Then this one, we're going to use number 5, the product rule, log of a squared plus log of b to the power of 4, same base, namely x. Finally, we use number 7, the power rule. We put the 2 in front, 4 in front, 7 in front. The final answer will be 2 log a base x plus 4 log b base x minus 7 log c base x. And we are going to move on. So in short, there are many properties of logs that are being used, and you got to be pretty comfortable with them. Log of square root of x cubed y to the power of 5. We want to expand it, we want to decompose it. So first, notice this is the same as x cubed y to the power of 5 to the power of 1/2. We use number 7 and we put the 1/2 in front. This one 3 comes in front. This one 5 comes in front using number 7. Then multiply it by 1/2. You get 3 halves log x plus 5 halves log y. By the way, again, reminding you, when we say log and there is no base, the base is 10. It's a common log. Natural log means the base is e. So simply put, we use number 6, the quotient rule, ln of the top minus ln of the bottom, ln of x minus ln of x squared plus y squared. Log base 4 of square root of x cube root of 10y z to the power of over z to the power of 10. So we can use any of those properties to begin with. Probably the best choice would be to start with number 6, log of the top minus log of the bottom, and both of them have the same base, namely 4. So log base 4 of square root of x, cube root of 10y minus log base 4 of z to the power of 10. Now we know square root of x is x to the power of 1/2, and cube root is 10y to the power of 1/3. So we change square root of x, we change 10 cube root of 10y. So we can separate this using number 5, the product rule, into 2 logs. Log of the first piece, x to the power of 1/2 base 4, and log of the second piece, 10y to the power of 1/3 base 4. Now first, this one has really 2 pieces. First, each one, 1/2 sits in front, 1/3 sits in front, 10 sits in front. We are looking at number 7, the power rule. So we're going to work on this one first, because this one, the 1/2 comes in front, becomes half of log x base 4. This one has 2 parts, 10 times y. And with number 5, we have log of 10 plus log of y, both of them base 4. So in other words, this part is log base 4 of 10 plus log base 4 of y. Now let's finish it off. 1/2 sits in front. Over here, 1/3 of log 10 base 4 plus 1/3 of log y base 4 minus 10 log base 4 of z. And that's the final answer. So we did it in a couple of, we used a couple of steps, although it can be done really in one step in essence. Condense to a single log. In other words, take it back, put them together. And so as you look at these properties, we can go from left to right, we can go from right to left. So in this case, we are going to move number 5 from right to left. So the product rule, I'm going to multiply these two. Log of 2x to the power of 4 times 3x to the power of 5. And the product of these two is 6x to the power of 9. So log of 6x to the power of 9. This one, I'm going to use number 6, the quotient rule. And I'm going to go from right to left. From right to left. ln of 6x to the power of 9 over x squared. And as you know, 6x to the power of 9 over x squared is 6x to the power of 7. So simplifies as follows. Let's see what we do here. First, I'm going to use number 7, and I'm going to go from right to left. In other words, we do get rid of the 2, and we put it here. We put it here. So we have we have log of x squared, and log of x plus 1 cubed. Now we go to number 5, and we go from right to left, and we say log of parentheses or brackets x squared times x plus 1 cubed. So that's pretty straightforward, everybody. Okay, what happens here is that first I want to put these two together because they both have a positive sign. Also, I want to get rid of the 1/2, put it here. So log x plus, okay, let's do this too. Let's get rid of the 3, put it here. So log x plus log z cubed minus log of y to the power of 1/2, that means square root of y. By the way, you may have to multiply to receive full credit as far as the exam sometimes. As far as I'm concerned, you're fine. So one more time, log x. This one is log of z cubed, and this one is log of square root of y negative. So these two would be log of x z cubed. This one, because of the negative, goes down. So the bottom line is log parentheses x z cubed. So maybe and minus puts this down here. So just in case. We want to solve exponential and logarithmic equations, reminding everybody, if a to the power of x and a to the power of y are equal, since they have the same base, they must have the same exponent. In this case, because they have the same exponent, must have the same base. We have the same base, so we must have the same exponent. These two must be identical. So we move things around as follows. So negative 3x is 3. Divide, and x becomes negative 1. (64 times 4 to the power of 3x equals 16). We want to bring everything to the same base. We notice that we can change the 64 to 4 cubed. This one is fine. This one is 4 squared. Now, according to the exponential rule, the left side would be 4 to the power of 3 plus 3x. And now that we have the same base, we must have the same exponents. Subtract, and you get negative 1. Divide by 3, and x is negative 1/3 as the final answer. And you can always put it back into the original equation and check. All right, 2e to the power of 3x equals 13, number 1. Divide by 2. And now, if you go with the definition, or just take the natural log, either way is fine. It means the same thing. The left side is 3x. The right side is natural log of 13 over 2. So what is x? One-third of the natural log of 13 over 2 is an exact answer. You keep it as an exact. If they ask you for a decimal representation and estimate is 0.62393. And how many decimals you carry? Whatever they ask you. In many cases, many, many decimals. What about e to the power of 2x minus e to the power of x minus 6? There are really two ways to do that. One is by substitution. If you let this one be x, my apologies, y. Let me just erase. If you let be e to the power of x be anything but x, because e to the power of x, this becomes y squared. So you can go with y squared minus y minus 6 and do the factoring. You want two numbers, the product is -6. And the sum is 1. So -3 and 2. Or you may recognize that you can factor it just the way it is. Right, e to the power of x minus 3 times e to the power of x plus 2. Please understand, if you go this route, it's really y minus 3, y plus 2. If you want to do the substitution, you don't have to. If you can do the factoring without the substitution, so be it. So e to the power of x is either 3 or -2. It can never be -2, but you take the natural log, or you go with the definition. Ln of e to the power of x is x, so ln3 is the exact answer, or with a bunch of decimals, an approximation 1.0986. And bear in mind again, e to the power of x is -2 has no solution, because if you go back to the graph of e to the power of x, that ranges from 0 to infinity. E to the power of x can't even be 0. So it's always a positive. We want to solve this, and same concept. When you're looking at logs, of course, remember the base must be positive, in this case a, and the argument must be positive, in this case x as well as y. And if two logs are the same, they must have the same argument, or if they have the same argument, the logs must be the same. So how do we deal with this? Anytime you have a log on one side and a number on the other, just all you have to do, go with the arrow. 9k is 3 squared. Which is 9, and k becomes 1. But by this case, whenever you have a bunch of logs and numbers, you bring all the logs to the same side, all the numbers to the same side. You don't have to move anything, because all the logs are on the same side. We are going to go with number 5, the product rule, and the left side becomes log of 4 times -5x, or log of -20x. And now we are going to go with the arrow. The base is missing. That means the base is 10. It's a common log. So the argument, -20x equals 10 squared. That's a common log, everybody. And so, of course, this is 100. And you divide by -20, x becomes -5. So the answer is -5. By the way, you have to check. This is fine. -5 makes this one positive, because the argument of log must be positive. That's why you check. Log base 7 of 5n minus 2 and log base 7 of 8 minus 5n are the same since they have the same base, and there is only one log on each side. They must have the same argument. 5n minus 2 and 8 minus 5n must be the same. And now you want to move things around as follows. So 10n is 10 and n becomes 1. And you check. If you plug in, you're supposed to get positive. 5 times 1 minus 2 is positive, 8 minus 5 is positive, and both of them are 3, by the way. In this case, again, you want to make sure we have all the logs on the same side, on the numbers on the same side. Because we don't have anything but logs, then we don't have to move anything. Each side, we bring the log into a single log. This one is done. This one, we bring it together using number 5, the product rule. Now, number 5, we're going to go from right to left. Log of x times 12, meaning log of 12x. Now we have a single log. By the way, the base is 10 because it's missing in action. So x plus 12 is 12x. So we get 11x divided by 12. X becomes 12 over 11. And if you put it here, positive, yes. Put it here, positive. Everything is fine. You can further check it, but just check to make sure the argument remains positive of each and every log that is involved in the equation. We have a natural log on both sides. We don't have to move anything. The right side is a single log, and we are done with that. The left side, we use the quotient rule, and we move from right to left. This is ln of x plus 4 over x. They both have the same base, namely e. Therefore, they must have the same argument. This is equal to this. And you do the cross product. This is x plus 4. This is x squared plus x. Instead of moving things around, just get rid of the common value of x. 4 becomes x squared. And x has two answers, positive and negative 2. We check. 2 works here is positive, positive, positive. Negative 2 is fine here. Messes up the second one. You don't even have to check with the last one. It's out. If any of those arguments is negative, you get rid of it. Log base 2 of x plus log base 2 of x minus 1 equals 1. When you have logs as well as numbers, if logs are on both sides, you bring them to one side. Well, you don't have to, everything is on one side. But if this was on this side, you would have to move it. And then all the numbers on the other side. Now, the side involving log, you have to bring it to a single, log. And we are going to use number 5, the product rule, log base 2 of x times x minus 1. And the right side remains unchanged. And now we go with the property of log. That means this arrow. X times x minus 1 is 2 to the power of 1. So this is x squared. This is minus x. Move this one, make it negative. And this is a simple factoring. You want two numbers. The product is negative 2. The sum is negative 1. So the numbers are negative 2 and positive 1. X is either positive 2 or negative 1. There are two answers we have to check. So if I put the 2 here, this is fine. 2 minus 1 is fine. If I put the negative 1 here, it doesn't work. I don't even have to check with this one. Negative 1 is out. We want to solve 4 to the power of x plus 10 equals 3. Move the 10 by subtracting. And 4 to the power of x equals a negative value, or even 0 has no solution because exponential functions, the range is from 0 to infinity. What about part B? Notice the right side is 1. And the left side is 7 to some power. So the right side can be 2 to the power of 0, 5 to the power of 0, 10 to the power of 0. But we choose it to be 7 to the power of 0. Why 7? Because the left side has base 7. But if you said 1 is equal to 5 to the power of 0, it's not incorrect. It just doesn't help us. Because both sides have the base 7, then the exponents must be the same. X minus 10 must be 0, which makes x equals 10. Now 4 to the power of x equals 9 to the power of x minus 2. We want to make both sides having the same base. We can't. Having the same exponent, we can't. So the methodology is to get to the exponent, you have to take a log. Whether you take a common log or natural log makes no difference. Here's the reason. If any of this have a base 10, you take a common log. If any of this has a base e, you take the natural log. Since they don't, it doesn't matter, your choice. So if we go with the natural log, you're going to take the natural log of both sides. This x sits in front, this one x minus 2. So please understand ln4 is a number, but we're going to keep it as ln4 because it's exact. Don't choose a calculator. So what is this guy? ln9 is a number times x, and then minus 2 ln9. Since we are solving for x, we are moving things around as follows. So it's 2 ln9. And so on the right side, we can factor the common factor of x. We get x times ln9 minus ln4. And divide both sides by the parentheses. You get x. Now this is an exact answer, everybody. You can put it into a calculator. This is an approximation. What I want to add is this. Right here, if we said instead of natural log, let's take a common log. If we go through the process over here, ln changes to log. Same thing here, same thing. And you end up with the same answer, by the way. log base b of 50, and we are assuming log 2 base b is a, log 3 base b is b, log 5 base b is c. So we're going to evaluate this, which means we have to factor this. And I hope you recognize this as 2 times 5 squared, 2 times 25. If you don't recognize it, remember the prime numbers are 2, 3, 5, 7, 11, 13, 17, and so forth. So you start factoring number 50, divide by the very first number that is divisible by, you get 25. Then it doesn't work, you go with the 3. Doesn't work, you go with the 5. And then you say 5, 5, 1, and this says 2 times 5 squared. So you, in order not to miss anything, you go from the smallest number and then move on to the larger numbers. And so what is this? This is log 2. This is 2 log 5. Both of them have the same base b. So this is log of 2. This is log of 5 squared. The 2 sits in front. Log 2 base b is a. 2 log 5 base b is c. So a plus 2c. It's very straightforward, everybody. We're going to continue with the same question. This time we are interested in log base b of the 5th root of 300. First, this means 300 to the power of 1/5. Second, according to number 7, the power rule, we can put the 1/5 in front. Now we have to factor number 300. Just a fast way of doing it, and then I'm going to show you with the factoring. Every 0, remember 10 is 2 times 5, everybody. 10 equals 2 times 5. So every 0 corresponds to 1, 2, 1, 5. There are 2 of them, so you have 2 2s and 2 5s. That means 2 squared and 5 squared. 2 squared is 4, 5 squared is 25, the product is 100, and 3. So you have 2 squared times 3 times 5 squared. But going back to the factoring, if you want to go through the process, you're going to write, and I'm going to erase it afterwards, 300. And you start with the, remember the smallest number is 2, 3, 5, and you continue, right? The smallest prime number is 2. 150, 75, 3, 25. Can I divide by 3 anymore? No. 5, 5, divide by 5. The moment you hit 1, you're done. And this is 2 squared times 3 times 5 squared. So this is log base b of 2 squared plus log base b of 3 plus log base b of 5 squared. This 2 sits in front, 2 sits in front. So we get, for 2 squared, we get 2 log base b of 2. For 3, we get log base b of 3. For 5 squared, we get that 2. 2 log base b of 5. And now each one is ABC. Plug in, and you're done. Okay. A nuclear reactor contains 200 grams of radioactive plutonium-239. Decays according to the formula A equals A sub 0, e to the power of negative 0.0000284T. And we use N of T equals N sub 0 e to the power minus KT in general. How much will how much will remain after 5,000 years? Find the half-life of plutonium. And so having said that, understand what's going on here. We start with how much? 200 grams, so that's A sub 0. What is T? In this case, it's 5,000. So we are going to use the formula with A sub 0 being 200 grams because they said so. And for part A, T must be 5,000. So let's replace the A sub 0 and replace the time. So A is 200, e to the power of negative 0.0000284, and then the T is replaced by 5,000. You multiply those two, you get negative 0.142. You raise e to that power times 200. You get 173.52 grams, which means if you have 2 grams of plutonium, a radioactive one, plutonium-239, 5,000 years later, 200 goes down to 173.52 grams. So I'm going to look at the half-life here, and I'm going to discuss the half-life in general when it comes to exponential growth. We have doubling time. When it comes to exponential decay, we have a half-life. In other words, how long does it take for this material to go down to half of its original size? 200 becomes 100. And it has got nothing to do with that, how much you begin with. So that's why we do a general format. When we go here, we replace the A with half of A sub 0. That's the meaning of half-life. You drop A sub 0 from both sides. And now, because the base is E here, we're going to take the natural log of both sides. And the left side is ln1 minus ln2, and the right side becomes the exponent, negative 0.40 and then 2840. So when you take the natural log of this one, you're left with the exponent only. So T becomes the, by the way, ln1 is 0. Everybody knows that, right? Becomes the left side minus ln2 over a coefficient of T, this number. And that gives us 24,406.59 years. Couple of notes. The continuous rate of growth is R or K, so n sub 0 e to the power of minus kt. So for example, would be the number that you have here, this one. The continuous rate of decay is minus R or minus K. In other words, both of them, you just keep the positive side. This negative means exponential decay. Okay, so the continuous rate of growth or decay, if they ask you, because when you mention growth, that means positive. When you mention decay, that means negative. Also, I want to look at the half-life in general. So if you look at this one and you want to calculate the half-life, the left side, n of t becomes half of n sub 0. You can drop n sub 0. And that's the point, that you really don't need to know what's the initial value, in this case, 200 grams. You don't need that. So now you take the natural log because the base is E here. Left side becomes ln1, which is 0 minus ln2. Right side becomes just the exponent minus kt. And t is ln2 over k, or k is ln2 over t, depending upon what they want you to come up with. If t which is the half-life is missing, ln 2 over k. If k is missing when the half-life is given, ln 2 over t. So it depends on what is given.